Part 4. Actually looking at solving more difficult transformer problems by using transfer and impedance method. So if we include our first little bit of a component on the left hand side, let's say Z, for argument's sake, Z1 there on the left hand side of that diagram is representing the resistance of the primary winding. Yep. So what you have to be aware of in these type of problems is that the only voltages that we could measure with a meter is the EG there connected at the primary terminals and the E2 there at the secondary terminals. Any other components that we add inside what is our model of a real transformer are going to be voltages we can't measure, but we may well need to calculate voltages and currents. So if about this problem we know EG, okay, and we know Z2, but we want to find out what the secondary voltage is and the secondary current, we've got a problem because we haven't got a way to factor in what this component is doing to the circuit. If all we've been given is that, because we can't use the as only this bit in that box there that is the ideal transformer. So the ideal bit happens between this voltage E1 and that voltage E2. But we're going to lose some of the generator voltage across that component there. That's the problem. That's why this is more difficult than a simple problem. Okay, so the method around that is, for this one problem, part 1, shift Z2 to primary. We know that Z2 dash is equal to A squared times Z2. Okay. Secondly, secondary voltage shifted to primary becomes E2 dash, which is equal to A times E2. Yep. We don't know it yet, but we can say if we put it on the primary side, that'll be equal to that. And 3, secondary current shifted to primary becomes I2 dash, which is equal to I2 divided by the turns ratio. So what we've done is our circuit in full now becomes this. There's our EG. There's our primary terminals. EG across them. Then we've got Z1 with I1 travelling through it. Okay. Then we would have here the secondary terminals with E2 dash, sorry, across them. Z, the impedance I squared Z2 or Z2 dash. Yep. And through that very same I1 current is I2 dash, which is equal to I2 over A. Okay. And just lastly, to complete that slide and those notes about that is, oh, hang on, for completeness, the transformer is here with nothing connected to it. Yeah? We've shifted everything from that secondary side to the primary side. So you can effectively rub all of that out. We've got a generator with a voltage we know. We've got an impedance Z1 and an impedance Z2 dash in series with each other, and one current flowing through them. That current is the primary current, but that primary current is also equal to the secondary current divided by the turns ratio. So we got a simple series circuit with a voltage connected to it now. The last thing you might have to do in some problems is, if there are more secondary components, move them in same way. And lastly, consider carefully whether complex values are required. Because transformers are made up of coils of wire or inductors, so you're likely to get, you might have connected capacitors, and the windings are made up of inductors even if you haven't got any connected inductance. Okay, so you may or may not have to consider, as soon as you've got mixed, as soon as there's a mixture, you've got an issue of complex values. Alright? You're happy with that as a summary of the method. Alright? But as always, method is best served by looking at an example. Okay? So this is the example we're gonna work through bit by bit, see if we can solve the problem. Generator voltage is 500 volts. Z1 is 10 ohms. Z2 is 5 ohms. Find the secondary voltage, E2, and the current, I2, using the shifting impedances method. Yeah. So where are we going to start with that problem? Yep. So tell me how I do that then, Luke. We call that Z2 dash, don't we? What's it equal to? Yep. And Mark made a good point with some of the younger students on degree the other day. With formulas, say them in your mind when you're writing them down. Every time you say it, as another route to committing that to memory in terms of repetition. So Z2 dash is equal to A2 Z2. So that's equal to 5 squared, because the A is 5, times 5 equals 125 ohms. Okay? And we also want to find E2, so we're going to find E2, we probably need to find E2 dash. So we'll make a statement here that it's A times E2, and I2 dash is I2 over A. But we don't know what they are yet. Yeah? So, here's our circuit with them shifted. We've got Z1, 10 ohms, Z2 dash, 125 ohms, E2 dash is equal to A times E2, and I2 dash is equal to I2 over A. Yeah. So, where do we go from there? Can we not we can forget that transformer now? All we got is that. We've got a single series circuit around there, haven't we? Two impedances in series connected to one voltage, 500 volts. So I mean, if it helps, you can just go. I got that, 500 volts, 10 ohms, and 125 ohms. That's what I've got. Yep. So what can I now calculate? Yep. If you want, just do a total impedance. That might be a way to go if that's a little bit more complicated circuit than this. So we could say that Z seen by the generator is equal to Z1 plus Z2 dash, 10 plus 125 is 135 ohms. Yep. Then we calculate a current, I1. I'm going to here say that it's also equal to I2 dash, because that's what we're really interested in. Yeah? And that's equal to EG over ZG. 500 over 135 equals 3.7 amps. Yeah. What can we find now? So we now know we've got 3.7 amps flowing in the circuit. What else are we aiming to find on the secondary side? Yeah, secondary voltage, aren't we? Yep. So we're on primary side only, so we can calculate E2 dash from we don't know E2 yet. That's what we're trying to find out, Luke. Do we know E1? EG. Yeah. We're interested in this voltage being dropped across that impedance, which is the secondary impedance reflected to the primary. Yeah. So if we can find this voltage here, we can reflect it back onto the primary with that formula, can't we? The reflecting back form. We've reflected it that way by multiplying by A. We divide by A, we can put it back over the other side. So we can find the value of E2 when it's on the primary side. We can calculate it back to the secondary side because we know this value is equal to E times the real value of E2. A times the real value of E2, sorry. What do we know enough to be able now to be able to calculate that voltage? If we've got the current going through a resistor and the resistor value, can we calculate the volt drop across it using Ohm's law? Volts is I2 dash the current times Z2 dash. 3.7 times 125 . .463 volts. Okay, so we've lost 37 volts across that little resistor. Does that look right? We've got 3.7 amps going through 10 ohms. We're going to get 37 volts drop across that resistor there. So it looks right because that voltage and that voltage, you've got to add up to that one, remember, by what law? Kirchhoff's voltage law. Yeah, so there's all these little checks to see, does it look sensible? And I'm emphasising this because working through the next problem yesterday in preparation for today, I actually used the wrong value. And then when I done my check at the end, I didn't tally up, and that might help me to find that problem because I'd done a check at the end. Okay, so just think, if you've got time, just does that look sensible? Do it all tie up with all the laws that I know? Okay, so now we know what I2 dash is and E2 dash. We can actually reflect back to the other side because we know that I2 dash is equal to I2 over A, therefore I2 is A times I2 dash, which is 5 times 3.7, and I made that 18.5 amps. Okay, so we calculated it on the primary side and then we transferred it back. E2 dash is A E2, therefore E2 is E2 dash over A, that is 463 over 5 equals 92.6 volts. Right?